Alright, so we're continuing 4.7. We're just doing some examples. And so here we have a cylindrical can. And the cylindrical can will have a fixed volume of 10 cubic feet. And we want to, or it holds 10 cubic feet, right? And uses the least amount of material. So we want to design such a can. So how should we start? Did you say draw a picture? Because that's the way we always start. For things that are that appropriate. So we'll just go ahead and say that that's our radius r, and our height h. Good. And then do you remember, or do you know the volume of a can? Here's a hint. It's the area of a face times the height. So the volume of the can is going to be pi r squared. Oops. Pi r squared h. Okay. Now we also need to take into account the surface area, right? Because that's the amount of material. And so the area, let's see, probably the easiest way to think about it is to cut the can open, right? So if I slice the can down here and roll it open, what do I have? This is going to have a height h. The length of this rectangle is the circumference, right? Do you remember the circumference of a circle? It's 2 pi r. Okay, and so the area is going to be the area of this plus the area of the top and the bottom of our can. So that's going to be 2 pi r squared plus 2 pi r h. Good. Now a is actually what we want to minimize. But notice that there are two variables here, right? The r and the h. However, the volume is fixed. And so using the volume equation, we can write either variable in terms of the other. We could write r in terms of h or h in terms of r. And so we would do that by taking the volume as 10 is equal to pi r squared h. And so, for example, probably the one we're going to use, right, because we only have the h there, is to say that h is equal to 10 over pi r squared. Okay, and then r is just a number that's bigger than or equal to 0. Good. Actually, it's going to be strictly greater than 0. But, you know, if the radius was 0, your amount of material would be 0, which may minimize things. Okay, I don't think there's any other constraint on r, right? R could be any positive number. Okay, so let's now put our two pieces of information together here, and a of r is now 2 pi r squared plus 2 pi r times 10 over pi r squared. Okay, which is 2 pi r squared plus, let's see, 20 pi. The pi's cancel. So that's just going to be 20 over r, I believe. Yes. And so now we differentiate as usual and find our critical points for pi r minus 20 over r squared. Set that equal to 0 and solve. So what do we get? Looks like I'll bring the 20 over r over the other side. 4 pi r is equal to 20 over r squared. So it looks like r cubed is equal to 20 over 4 pi, or 5 over pi. Good. And so therefore r is equal to the cube root of 5 over pi. Good. Now, we don't have any endpoints, so how am I going to tell if this is a global maximum or global minimum? Well, our radius is going to be all the positive numbers, right? And so we can look at the sign of a prime to see what the signs are. And so if our radius is here at the cube root of 5 over pi, and I plug in a number that's less than that, so let's say the radius is 1, right? So That would be 4 pi is about 12 minus 20. That's going to be negative. And so a number bigger than the cube root of 5 over pi. Uh, How about, by the way, that's about 1.17. How about like 2? So if r is equal to 2, then this is going to simplify to 5, and then that's going to be 8 pi, so that's going to be positive for sure. Okay, and then it'll remain positive throughout, and so that means our function is decreasing globally all the way down to the cube root of 5 over pi, and then it increases forever after. And so therefore we can conclude that the minimum area occurs when the radius is the cube root of 5 over pi. Good. Notice, I need to get my height too. And so the height is approximately going to be, I'm going to plug that into my calculator. R is approximately 1.17, and H then is going to be about 2.34. Whoops, 2.34. And so that gives me the dimensions, right, of the can, that so that the surface area using the Kansas minimum. Good. All right. So that's that with that one. Maybe I'll pause here, and we'll write down a new problem. Okay, so now we're going to try to find the maximum area of a rectangle inscribed in a circle of radius 1. So the first thing we need to do is to draw a picture. I need a circle of radius 1. So there's my circle of radius 1. And to inscribe a rectangle, we'll assume that things are parallel to the axes. And so there's a rectangle that's inscribed in the circle. And I think the key part of this problem is to be sure that we're labeling x and y correctly. So this, let's call this point right here the point xy, right? So that means that this length right here is x, and the height here is y, right? And that's important because using this x and y, you can say that the radius, or the circle equation, is x squared plus y squared equals 1, right? And so this is giving you the relationship between x and y. Secondly, we have our area of the rectangle. And we see that the base here is x by, 2x, and then the height is going to be similarly 2y. So the area is 2x times 2y, or 4xy. Good. And so we want to maximize our area such that x and y lies on the unit circle, so x squared plus y squared equals 1. And so again, do you see what's happening? We have a function of more than one variable, but we have a side constraint, and so we make a substitution of the side constraint into the function, so we get a function of just one variable. Good. And so therefore, I guess I can call this a here. And so what can I do here? I can write y as the square root of 1 minus x squared, right? And so therefore I can now write my a as 4 times x times the square root of 1 minus x squared. Any restrictions on x? From the picture we see that x has to be between 0 and 1. And so we're back now to a closed interval method problem, right? And so what do? We check endpoints and critical points. And what happens at the endpoints? A of 0 is equal to 0. That's not very exciting. A of 1 is equal to 0. That's not very exciting. But that tells you that if you only have one critical point in the interior, that's got to be your max, right? And so let's go ahead and check that. So take the derivative of a with respect to x and set it equal to 0. Notice that that is a product rule, right? So that's the derivative of x plus 4x times the derivative of the square root part. And don't forget the chain rule. Good. So then, let's see. I'm going to rewrite this using a fraction, but let's see what my fraction needs to be. So the 2's cancel here. I'll have a minus 4x, it looks like. Right? And so 4x squared minus 4x squared divided by the square root of 1 minus x squared. Good. And so I'll multiply top and bottom of this by square root of 1 minus x squared. Right? So that's a times, or not a, that's 4. 4 times 1 minus x squared minus 4x squared. All divided by the square root of 1 minus x squared. Very good. So now what? It looks like I can factor things out a little bit. Maybe I'll write that as 4 times 1 minus 2x squared over square root of 1 minus x squared. Let's set that equal to 0. And you can see what we need then. So that means that 1 minus 2x squared equals 0. Or x squared equals 1/2. Or x equals plus or minus 1 over the square root of 2, but we only take the positive 1. Good. And of course, if x is 1 over the square root of 2, y is equal to 1 over the square root of 2 as well. And so those are the dimensions that we'll use for our rectangle. And we already know that it's going to give us the maximum area, but did we need to find the area? I think it does. I think we do need to find the area, right? Because we're finding the max area. So the area is 4xy. And so area is 4 times x times y, 2. Very good. That is our maximum area. All right. So I'm going to stop the video here. We've had a couple of examples. Do you want one more? I think I've got one more in me. So we'll try one more video of a couple of examples. See you then.